Alright, today it's another out of sight chemistry video. Today we're going to be talking about substitution and elimination reactions. Substitution and elimination. Substitution is a reaction that happens when you remove a leaving group from the molecule and replace it with something else. And an elimination is when you eliminate the leaving group altogether and create a double bond. Those are two really basic mechanisms that are frequently seen in organic chemistry. So there are two kinds of elimination and substitution each. There's SN2, E2, SN1, and E1. First, let's talk about the requirements for each. So when you have a primary alkyl halide, basically it's a carbon attached to a halogen, and to just one carbon. So this carbon is attached to other carbons, but it's still just one carbon. This is our carbon right here in this circle. That's the carbon that we're looking at that is primary. This is our secondary carbon right there, circle to demonstrate that that's our carbon. This is our halogen and our two carbons, and that's why it's secondary. And this is tertiary, where it's a carbon attached to three carbons and a halogen. So you have to do, when you have a primary alkyl halide, you can do either SN2 or E2. The requirements for these two are SN2 occurs with a good nucleophile and a weak base in a polar aprotic solution, in a polar aprotic solvent. And E2 occurs when you have a strong nucleophile and a strong base, and you have heat applied to it. I use good and strong interchangeably though, just so you guys know. For SN2, in the secondary alkyl halide, you can do SN2, E2, SN1, or E1. You can do all of them. SN2 with a strong nucleophile weak base, E2 with a strong and nucleophile and base, and the base is bulky and you're applying heat. SN1, you have a weak and a weak, and it's polar protic. It's polar protic. E1, you have a weak nucleophile, weak base, and you add heat. So basically for the eliminations, you add heat. That's the difference, the only difference pretty much between E1 and SN1, because they're pretty much the same requirements except E1 has heat. Tertiary alkyl halide, E2, SN1, and E1. We see the same things again with E2 needing a good nucleophile and a good bulky base. SN1 is a weak nucleophile, weak base, and polar protic. In E1 is weak, weak, and heat. And now it's time to go over the steps for these. So in SN2, let's say that we have this, let's say we have this carbon, and it's attached to bromine, which is a halogen, and it's therefore a good leaving group. And we have attached, let's just say we have this, and we have this. Doesn't really matter much what we have attached to it other than that. And then let's just put we have a good nucleophile. It really doesn't matter what it is. It could be OH or whatever. So what we're going to do in SN2, it's a concerted mechanism. So we're going to see two things happen, and they happen at the same time. When this attaches here, the leaving group leaves. And then we add an arrow to indicate the next step. And we have the nucleophile, which isn't a nucleophile anymore because it's attached to the carbon. And we have Br minus apart from it. What happens here is that we have an inversion of stereochemistry, so everything kind of just shifts a little. Okay, so in E2, what we have is we have let's do it like this. All right. So we have a carbon attached to a carbon, and okay, let's do H, 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 and then here we can do, okay, yeah, CH3. Yeah, it doesn't really matter. Let's do H. Just keep it the same throughout, even though it really doesn't matter. We have H and we have Br. It's a leaving group. I hope you guys are thinking halogen leaving group. So here we can have an OH. And what happens now is that, again, E2, same as SN2, is going to do a concerted mechanism. This all happens at the same time. It attacks the hydrogen, and then the bond goes over here to become a double bond. And so the leaving group leaves. Actually, let's be careful with our arrows and indicate that this goes to bromine and not the electrons. Now we do an arrow to indicate what happens next. And what happens next is that we have carbon double bonded to carbon. And then we just have H, 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 H. Okay, fantastic. Now SN1 is different from from SN2 in that it has 2 steps. All right, so we have step 1, bond heterolysis, or the breaking of the bonds. This first step is going to be your rate determining step. It's your longest step in the whole thing, and the other steps are going to be faster and quicker, and basically this is the step that determines what the mechanism is, how it's going to proceed. You don't really need to know that, just know that that's the first step is rate determining step, and then you display that with the energy diagrams. So here we have C, yeah, let's do CH3, 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 and let's, instead of Br, let's do Cl, just to change it up a bit. So this goes here, and it just breaks off, because it's a leaving group, it's a halogen, so it's a leaving group. This is our rate determining step, and what we get is CH3, C, CH3, CH3, and then we have a plus charge because it left and took its electrons with it, so we have a plus charge. And we have Cl minus charge. Now what we have here is we have a tertiary carbocation intermediate formed from our tertiary alkyl halide. So that's important to, yeah, since the reason that this is tertiary, so that's why we do SN1, whereas this one was, this one was secondary. All right, so and so was and this one was just primary. All right, so let's go here. So our second step is going to be nucleophilic addition. we're going to attack it with our nucleophile, or attack our tertiary carbocation intermediate with our nucleophile. So we have C, CH3, CH3, CH3 plus, and we have our OH2. This is our water. No, wait, it's not gonna have. There you go, not that much. All right. So it just attacks, boop, attacks the carbon right there. Now what we get is C, CH3, 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 and then we have O, H, H. And now we do our third step, proton exchange or deprotonation. So let me just put step 3, deprotonate. It's going on from the side. Doesn't matter, we're fine. Can't even read it because my handwriting is sloppy. So I'm sorry about that. All right, so we got another H2O. And you want to indicate the movement of electrons and draw the electrons every time. Don't go sloppy and be like, nah. All right. Or whatever. Yeah, this has a positive charge. So you make the movement of the arrows indicate that the bond is going toward the oxygen. And this indicates CH3, CH3, CH3. I'm not showing actual stereochemistry. I'm just doing it because it doesn't fit. OH and H3O plus All right, so that's our SN1 mechanism. Now E1 is similar to SN1 in that it has multiple steps. It's not just one step like SN2 or E2. And it has even the same conditions, but it competes with it with SN1 in that we know that it occurs when we have heat. Usually they'll indicate that in the beginning when you have your starting materials with the arrow, and they'll put a triangle or heat or something like that to indicate that you have heat. Or if the problem says there's heat in the reaction, then you know it's elimination. So let's go here, competes with SN1, and we have, let's do C, CH3, CH3, I made that clear, it's a C, not an CH3, and let's keep using chlorine. All right, and it leaves just like before. All right, so I'm tired of drawing CH3, so I'm just gonna, you guys know what that means. Okay, and we have our Cl minus. Now this is the leaving group leaving. That's the first step. So it's basically bond heterolysis again. And now our second step is just deprotonation. Let me write that out. Step 1, bond heterolysis. And now step 2, deprotonation. So we have our H2O, and we have our, I'm gonna have to write out our hydrogens now, I guess. All right, let me just do that. And then here I have H. So it goes over here. that correct? Wait a minute. Okay, so this is the carbon with the positive charge. This carbon is going to be our alpha carbon. That's an alpha symbol-ish. And so we're going to look for our beta carbon, which is this one right here, the carbon it's attached to. If we had more carbons, then we would, like if this was a secondary carbocation, then we would look to the two carbons and determine which one takes priority for doing this reaction, or if both have the same amount of priority, and then you end up with, you know, two different products of equal amount. So yeah, then you pick which one of these hydrogens, which one of these beta hydrogens you want to use, and then you basically just continue the reaction normally. So we end up here, yes, we get H3O plus, and we have this. That's what we end up with. So basically that's how you do E1, and that's all of the steps for these mechanisms.